A baseball is thrown at a speed of 30 meters per second at an angle of 45 degrees. It lands on a flat roof of a 13-meter tall building. The ball is thrown from a height of 1.0 meters from the ground. Find A, horizontal displacement, and B, the vertical component of velocity just before it strikes the ground. So step 1 of the problem is to draw a diagram of the projectile motion. Notice how it's not drawn to scale, however, but it does indicate the initial height and the final height. Also, since the object doesn't start from the ground and end on the ground, notice how it's not the shape of a complete symmetric parabola to describe the motion of the projectile, rather only a partial asymmetric parabola. Therefore, we cannot simply find the time required to reach the maximum height, the vertex, and simply multiply it by 2. So when this occurs, we're required to apply the quadratic formula. So I love this problem, and it's a great introduction, and it's a great challenge question too. So notice the underlying theme. They say find the horizontal displacement. We're trying to find x. And the common pattern or theme, especially in physics 1, is that you have 2 unknowns. You hit a roadblock. In order to find x, I need to find t. So we apply this quadratic kinematic equation. Final height minus initial height equals vi sine theta t plus 1/2 gt squared. Again, notice they said the initial velocity was 30 meters per second. The initial height was 1 meter. The final height was 13 meters. And the angle theta was 45 degrees. So you plug in 13 minus y initial, which is 1, equals 30 sine of 45 degrees times t plus 1/2 g negative 9.8 times t squared. This becomes 12 equals 21.2 times t minus 4.9 t squared. Next, another recurring theme in projectile motion is that usually y final is 0 and y initial is 0. They're both the same value, or it could be y final is 4 meters, y initial is 4 meters. So you'd get 4 minus 4, which is 0. Anyways, whenever the left-hand side equals 0, you can just solve this by factoring. But when the left-hand side is a number other than 0, you have to apply the quadratic formula. So write this in descending order. Which entails we also move the constant to the other side. So subtract 12 to both sides, which sets the equation equal to 0. So once the equation's in descending order, which also entails it's set equal to 0, you can appropriately label and identify your A, B, and C. So the quadratic formula is negative b plus or minus the square root b squared minus 4ac, all divided by 2a. So this is negative b, which is 21.2, plus or minus the square root b squared minus 4 times a, negative 4.9, times c, which is negative 12, all divided by 2 times a. This becomes negative 21.2 plus or minus the entire radicand becomes 214.24, all divided by negative 9.8. Perfect. And this is equal to 0.673 seconds or 3.65 seconds. Now, I love this problem because normally the recurring pattern in physics is that you get a negative and a positive value for t, and you reject the negative value for time since it has no physical interpretation. But there are other cases where you could just get a small positive number and a larger positive. So the t value will be the larger of the two numbers. Finally, remember, we went off on that tangent to solve for x and use the equation x equals v initial cosine theta t. So that's 30 cosine of 45 degrees times the time we found. This gives a horizontal displacement, x equals 77.4 meters. Excellent. Wonderful. So we used this one kinematic equation pertaining to x, and we used one of the kinematic equations pertaining to the y direction. Next, for part B, the vertical component of final velocity, we'll use a second out of our three kinematic equation that pertains to the y direction. And I'll use this one because it's already isolated for y. The final velocity in the vertical direction is vi sine theta plus g times t. No algebra required. It's already isolated for the desired quantity. initial velocity sine of 45 degrees plus g, which is negative 9.8, times t, 3.65. So the final velocity in the y direction is negative 14.6 meters per second. And you can check your work. Notice how a negative velocity makes sense at this point because we're moving down when we're about to strike the roof of the building. So let's solve this one last way. Let's do an alternative solution for part B, because notice there's a third kinematic equation pertaining to the y direction that we haven't applied yet. And it's just as equally acceptable to use that one. So if you were solving this problem and you chose to use this kinematic equation, final velocity in the vertical direction squared equals initial velocity squared sine squared theta plus 2g y final minus y initial. This is equally acceptable and great. It just requires us to do some algebra at the end. Let's see if we get the same answer so we can check our work. 30 squared sine squared of 45 degrees plus 2 times g, negative 9.8, y final minus y initial. Again, some of the textbooks, when they first introduce you to kinematic equations for linear motion, one-dimensional motion, they use a plus sign. So I like to keep that same formula. I write the kinematic equation the same, but with a plus sign. Some textbooks, however, when they introduce projectile motion, they change this to a negative sign to take into account the sign for g. And I despise it because now we have a minus sign instead of a positive. So then we have to remember to plug in a positive 9.8 instead of a negative. But in reality, g itself isn't positive. It's just that they already took into account the negative sign and it's all the way over here. So again, if the textbook wrote minus 2g, that minus sign technically does belong to the 9.8. And it is so confusing because then students are saying, do I plug in a positive 9.8 or a negative? So here's our sign for g, negative. And once we calculate this, we get 450 plus negative 235.2. So this gives 214.8. Oh yes, and let's remind ourselves, this is not v final. This is v final squared. So to isolate the velocity, I square root. Whenever you square root both sides of an equation, you have to tack on a plus or minus. So final velocity equals, again, 14.6. The same result as we got before. And now, out of the plus or minus, I know, well, the object is falling, so I tack on a negative in front. Just by understanding the physics of the situation. It's moving down. And that's how you approach a projectile motion problem.